Internal developer platforms, or IDPs, are not hard to create. Anyone can do it, as long as that someone knows everything about everything. Today I will show you everything you should know about developer platforms. We'll go through all the principles behind them, through all the components they should have, and I'll even show you how to build one. This will be a tutorial on how to build a platform in 5 mandatory and 1 optional step. At the end of today's journey, you will have a fully operational IDP with everything you might need. Most likely. Welcome to DevOps Toolkit, the channel where months of work are condensed into minutes. Today's video is special. It is a result of months of work. Quite a few topics I explored in previous videos had a hidden agenda. They were pieces of the puzzle I was trying to assemble, and that puzzle is now complete. That puzzle is a full internal developer platform, or IDP. Hence, today we will explore everything you need to know to assemble a fully operational platform. Now, before we proceed, let me tell you the only requirement I had when I embarked on this journey. Everything needs to be open source. When possible, projects we'll use should be in a foundation like CNCF or CDF or any other. If that is not possible or not practical, we will resort to a non-open source solution, but if that happens, it needs to be at least free. So the only rule is that it should be open source, preferably in a foundation, or free. During this video, we will see a tool used for each of the categories, but I will give you the alternative solutions that should produce a similar result. So you should be able to switch those I used if, for some reason or another, my choice does not fit your needs. There are, of course, objectives as well. Actually, there is only one objective. We'll create a platform that will do everything that needs to be done related to applications. Now, when I say applications, I mean everything required to deploy and observe applications. That means Git repositories, manifests, scripts, workflows, databases, policies, and everything else that might be needed. Finally, even though this might be longer than the videos I typically release, I might not go into details of everything I will explore today. If I would, the video would never end. I will, however, provide links to videos with more detail about a specific tool, the reasons behind certain choices, and everything else we'll go through today. As I already mentioned, this video is the end result of quite a few other videos. They were my way of exploring various combinations that led me to what you will see today. Finally, everything we'll do today will be more or less easy. The challenge is not necessarily in learning specific tools, but rather in making the right choices and knowing how to combine them. So, let's do it. Let's build a fully operational internal developer platform that will have everything a platform needs to have. We'll take a quick break for me to introduce you to KodeKloud, the sponsor of this video. Here it goes. You're probably watching videos on this channel because you want to learn, and I do my best to share experience. However, my videos are chaotic, mainly because I am chaotic. I speak about things I work on and share what I discovered. I rarely try to provide a course on a specific subject. You obviously like that since you are watching one such video. Sometimes, however, you might benefit from a more structured learning experience. That's where KodeKloud comes in. KodeKloud is an engaging learning platform with over 120 premium courses that come with hands-on labs. They have dedicated learning paths catering all levels of learners, from beginners to advanced. Moreover, they have a very active DevOps community which helps users get quick solutions to their problems. And here comes the best part. They are offering all their courses for free from 10th to 17th of February. All you have to do to get them for free is to head to KodeKloud using the link in the description or on the screen. Big thanks to KodeKloud for sponsoring this video, and now let's get back to the main subject. Let's start with a brief explanation of the principles I believe should be followed when building a platform. A platform is a set of services. AWS is a platform, and it is a set of services. The same can be said for Azure, Google Cloud, or anything else. Those services can be anything. It can be applications, databases, clusters, or anything else. It's something as a service that is consumed by engineers in your company. The reason we might build our own platform is to make it fit our needs. Cloud providers are generic. They tend to provide solutions that fit everyone's needs, and as a result of that objective, they tend to have components designed to be lower level than what we might need. If we build our own platform, we have the opportunity to make it very specific to our business and the way we operate. Services that compose a platform are created and maintained by some and consumed by others. We'll call those who create and maintain services owners, and those who consume them consumers. The latter is typically other developers. Now, the question is, how do people consume services we are making? To find the answer to that question, we can take a look at how platforms from cloud providers are accessed. All of them, and I repeat, all of them allow us to access their platform through the API. Now, you might say that's not the case. You might be using a web UI to access AWS. You might be using GCloud CLI to interact with Google Cloud. You might be writing Terraform modules to manage Azure. Here's the thing. All those are tools that interact with the platform through the API. Some of them might be created and maintained by providers themselves, while others, like Terraform, might be done by other companies or communities. APIs are what enable those tools to exist. So, when building an internal developer platform, we expose our services through an API, and others consume it through that same API, directly or through some other interfaces like web UI, CLIs, and so on and so forth. Next, we should talk about operations. There are two major types. There is state management, and there are one-shot actions. State management is all about defining the state of something and having a process that maintains that state. We define what it is, its desired state, and a service in the platform ensures that state is what it should be. That can be an application, a database, a cluster, or anything else. Those services should essentially ensure that the desired state is maintained forever and ever, or until we change it. If an application stops working, it should be started again. If a node in a cluster fails, a new one should be created and added to that cluster. You get the point, right? A great example of state management is Kubernetes. When we define through, let's say, deployment, that there should be 5 pods, Kubernetes will ensure that there are 5. If there are 4, 5th one will be created. If there are 6, one will be shut down. There are controllers that are ensuring that the actual state is the same as the desired state. It's ensuring that the contract between us and machines is enforced. Then we have one-shot actions. Those are operations that we perform once and only once. In the past, that would be everything. Before we started managing the state of resources, we were performing one-shot actions. We would SSH into a server and start the process of our application. If that application goes down, well, tough luck. It would be brought back up only after our users start complaining, and Joe, the person who deployed it, comes back from his vacation. Now, we don't use one-shot actions for that anymore. Instead, they are now reserved for operations that should be performed once and only once. Running tests when we push changes to a repo is one-shot action. There is no point running them many times for that commit, unless we wrote flaky tests that sometimes work and sometimes throw false positives, but let's not do that. Similarly, we build container images only once for a release, and so on and so forth. Both state management and one-shot actions are managed through the API. We tell the API what we want, and it makes it happen. It creates and manages the state of a database, or it runs a workflow that performs one-shot actions that represent our CI process. Now, for such an API to work correctly, there must be some rules, or to be more precise, access control and policies. For example, only allowed types of resources can be accepted. If you want a database but databases are not offered as a service, the API should reject it. If that's not the case, if there is indeed such a service, it should validate that the information provided is correct. If you specify that we would like to be, let's say, in the Iceland region, and there is no such region, a policy should reject it. If the type is not the correct one, it should be rejected as well. All those we discussed so far are mandatory, at least if we are building a platform in this century. If you have a time machine and you're living in the past, that might not be the case. Back in 20th century, you might rightfully disagree with one, if not more, of those premises. For those of us living in the present, in 21st century, those are non-negotiable components of a platform. There must be an API through which people will interact with services. There must be both state management and one-shot actions. And there must be some policies that prevent us from trying to do what cannot be or shouldn't be done. Then there are optional components, mostly related to more user-friendly ways to consume services. There can be a custom web UI, or a CLI, or a VS Code extension, or anything else. Now, you might say that's not the case. You might proclaim any of those mandatory, but I disagree. They are not. Services in the platform can be consumed through the API. One could send a request to it with CURL, or wget, or kubectl, if it's built on top of Kubernetes, or through someone's code, or a script, or anything else. If you do choose to build a web UI, or a CLI, or an IDE extension, or anything else, we are making the platform more user-friendly. We make what was already possible easier and nicer. Today we'll do all of it. We'll implement both the mandatory and optional components. At the end of this video, you'll have a fully operational platform that can be extended to meet your specific needs. We'll do all that by adopting certain tools, but you won't be limited to those I selected. I'll give you the alternatives. So if you disagree with one or more of my choices, you will know what can be used instead to accomplish a similar, if not exactly the same, objective. And here comes an important note. What comes next is a condensed story. I already published videos that go into more details about each of the components. If you watch them, you might notice a bit of repetition, or to be more precise, you might feel like you're watching a summary of what you already saw. Today's goal is to combine it all together. I'll try to be as fast as possible. You feel free to skip a section or two if you saw those and end up being bored. Timecodes are in the description. If, on the other hand, you haven't seen those videos, this is a good starting point, and I'll provide links you can use to explore more details. That's enough of a chit chat. This will be a long one. The sooner we dive into it, the better. We'll use Kubernetes to build the API. No other choice makes sense today, given that Kubernetes is widely used and at the same time provides everything we need to build an API through its custom resource definitions. There are many ways we can create CRDs. We can simply write a YAML representation of the CRD definition. That's easy, but given that we might need also to tell it what to do when a custom resource based on that definition is created, we might need to also create controllers. We could do that by writing Go or code in any other language, but that might be too cumbersome. Instead, we can use one of the tools that enable us to create CRDs and controllers. We'll use Crossplane today, mainly because that's the tool I'm using the most. You don't have to choose it. There are many alternatives, and if you're looking for one, I strongly suggest checking out Kubevela and Crow. This video is not about comparing those tools, nor any other, but rather showing what we might have to do and how to do it. Every phase of what we're building can be done with multiple tools, and I encourage you to try at least two before making a decision which one to use. The important part is that you will find links to videos that go into more detail about all of them in the description. Here's an example of a crossplane composite resource definition that extends Kubernetes API by creating a CRD. That's a CRD that defines an interface people can use to manage applications. It defines fields like image, tag, port, and others, with types of data that can be used like string, integer, boolean, and others. There is also a specification of which fields are required, additional status information, what will be printed on a screen, and so on and so forth. I already applied that one and a few other crossplane composite resource definitions, and we can confirm that they extended Kubernetes by listing all CRDs and filtering the output with grep so that only those that I created are shown. As a result, people will be able to consume services like app, GitHub, and SQL by telling the API that's what they want. Actually, that's not really true. Creating a CRD extends Kubernetes API by creating a new custom endpoint. By itself, a CRD is almost useless. If you send a request to the cluster to create a resource, all that the API will do is publish an event saying, hey, someone just created a resource of this kind. If there is no controller listening to those types of events, nothing will happen. The API has no idea what should be done. It only knows how to accept requests for known endpoints and, if they're valid, publish an event announcing that a new resource was stored in its internal database. We'll get to the part of doing something with those requests later. For now, what matters is that we extended Kubernetes API. And here comes the question though. Why do we want APIs in the first place? We already talked about one of the reasons. That's how people and tools interact without services. There is a second reason though. APIs can be discoverable. That's certainly the case with those built on top of Kubernetes. Discoverability is important since that means that we can define something once and only once and let any tools we might be using discover schemas. Backstage, for example, can be extended with a plugin so that it discovers Kube API schemas and converts them into Backstage components. That saves us time since we would essentially need to write the same definition in different formats. One for a UI, one for a CLI, and so on and so forth. Instead, with APIs like those we just saw, we can simply say, there's the API, figure it out. Here's an example. kubectl has no idea what is upclaim. However, as we just saw, it can go to the API and ask for its schema and do whatever it needs to be done with it. We'll see API discoverability in action later. Right now, we'll jump into the next component of the platform we are building. State management can be defined as contract enforcement. We can say something like, I want this. Don't ask me how it should be done, just do it and make sure that it will run forever and ever. From there on, it's up to controllers to figure out how to ensure that the state we want is the state that actually is and that it stays that way forever and ever. Any Kubernetes controller, unless done badly, is managing state. The one in charge of deployments is managing the state of deployment resources. The same goes for controllers in charge of replica sets, pods, stateful sets, or any other. However, since we are building our own APIs, we need our own controllers, or as some might call them, operators. The question is what those controllers should do. Now, to answer that question, I will assume that you already have means to set up and run low-level resources like containers, networking, VMs, and so on and so forth. If that's the case, the job of the controllers we're building is relatively easy to define. They should compose resources based on users' inputs. They should convert user-friendly abstractions we're creating into low-level resources. The same tools we can use to create CRDs can be used to create controllers. That could be Crossplane, kubevela, Crow, or any other. There are plenty of choices. Today, however, we'll continue using Crossplane for that since it's what we started with. Now, I will not go into details of how I created Crossplane compositions nor the details of what service consumers, developers should do to use them. I already explored it in that video over there, so I'll go through it fast. Today's objective is to see all the components combined, and if you think that it all makes sense, you can watch that and other videos I'll mention in more detail. Let's say that they, developers, or somebody would start working or want to start working on a new application. What would they need first? Obviously, it's a Git repository with some initial bootstrap code. Here's how that first step would look like in the form of a custom resource based on CRDs and controllers we provided. Over there, a user defined a GitHub claim resource that should create and manage a repository IDP full up. That repo should be public and should have whatever is needed to start working on Go applications. Easy, right? Later on, we might discover better ways to apply that resource. For now, a simple kubectl apply should do. Through those few lines of YAML, we got the repository, a branch, a few files, and a pull request. It should be everything one might need to start working on an application. To begin with, let's clone that repo, enter inside the local copy, merge the PR, and pull it into the local copy. From here on, the developer would write code until it's ready to be released, whatever ready means. Now, code alone is not enough. We need to define quite a few other things before that application reaches production. To begin with, that application might need a database, so let's focus on that. Since we are building a platform, consumers should be able to get database servers without going through the suffering of assembling all the pieces required to run it. Since we already have a composition for that, a user can start by creating a new directory where the manifests will be stored. Next, they would write a few lines of YAML, but to make it easier for this demo, I already prepared them, so let's just copy them into a newly created directory. As I already mentioned, you can see more details in that video over there, so we'll skip the chit chat and apply the password. The second manifest, though, is more interesting. that one is definitely more interesting one, right? Over there we specified that we would like to create an instance of SQL claim which will create and manage everything required to run PostgreSQL database server in Azure. That should be version 11, it should be small, whatever that means, and it should be running in the East US region. Inside that server there should be two databases, DB01 and DB02. Still very easy, right? Yeah, let's just apply it. The controller in charge of the resources of that kind is now working on creating and managing all Azure, AWS or Google Cloud resources. It depends on which hyperscaler you chose, as well as two databases inside the server. The only thing missing for now is the application itself. So let's copy the definition I prepared and take a quick look at it. You can probably guess what we'll get by looking at the parameters. It will be a set of Kubernetes resources that will form an application connected to the DB we created earlier. It will also push some additional files to the repository, and it will enable CI process for that application. So let's just apply it. That should have created everything we might need to work on an application connected to the database. In this specific case, that means not only the resources in Kubernetes, but also quite a few other things that are not related with state management. We'll explore those later. For now, let's take a look at some, if not all, of the resources that were composed for us. The important thing to note is that the pod is not ready. It is failing with a message error image pool. That was to be expected, since we did not yet build the image with the first release of our application. To do that, we need to switch from state management to one-shot actions or workflows. One-shot actions or workflows can be explained as steps that need to be executed once and only once every time we change something somewhere. That something is typically code, and that somewhere is usually a Git repository. Unlike state management, that is a contract of sorts where machines promise to manage actual state of resources, one-shot actions typically validate changes we made and produce some artifacts like container images or new manifests. We already saw an example of an action that we are missing. We deployed an application without building a container image first. Fortunately, we already have everything we need to remedy that. There are probably more workflow or CI or whatever we might call tools that execute tasks than any other type of tools. We can use Jenkins or GitHub Actions or Tekton or Argo Workflows or CodeFresh or Circle CI or GitLab CI or any other out of dozens, if not hundreds, of tools. At their core, they all do the same thing. They can execute tasks sequentially or in parallel, and those executions can be triggered by some events, mainly Git webhooks. If we exclude some bangs and whistles, the tools in that category haven't fundamentally changed since Hudson, which later became Jenkins. We'll use GitHub Actions today, mostly because open source options are too cumbersome to set up and maintain. It's free, at least for public repos. Since the repo we are using today is public, it is the most convenient choice. When we applied the upclaim resource, Crossplane composed not only Kubernetes resources required to run the application, but it also created a new PR in the repo with all the files needed to run a CI workflow. Here's the proof. We got CI YAML and sync control plane direct YAML definition that represents GitHub Actions workflows. The second one is irrelevant since it's a leftover from a different scenario that I forgot to remove. The CI YAML file is what matters since it contains the workflow which will, among other things, build a container image we are missing. There is also a Docker file, which everyone should know what it's used for, devbox CI JSON with Nix packages with all the tools we'll need for the actions we'll execute, and finally nushellscript.nu, which contains the actual tasks we'll run. If you're not familiar with Nushell, especially not in the context of it being used as a CLI, please watch that video over there. So let's just merge that PR and pull the latest revision of the repo. And now we can see the workflow in action. All we have to do is push some changes to the repo to trigger it. Since we already made a few changes, we can just add, commit, and push them. That should have triggered a GitHub action run, so let's see how it's going. CI workflow run was executed successfully. It ran tests, built a container image and pushed it to the registry, and finally it updated app claim definition and pushed it to Git. And we can confirm that by pulling the latest version of the repo and taking another look at CLI demo YAML. We can see that the tag was updated, and now we can reapply that manifest to the cluster and take another look at what's inside the A-team namespace. And look at that. We can see that the pod is now running. We just saw not only that one-shot actions or workflows are necessary, but also that all the files needed for it can be done without any additional effort by users, by portal consumers. It was all a part of defining the application. Now, that was arguably the worst way we could define and apply services. We'll see better ways later. For now, let's delete the app since we applied it without any validation. The last mandatory piece of the puzzle is RBAC and policies. We need to ensure that only those who are allowed to use the cluster are able to use it. And we need to ensure that only valid requests to the API are processed. We solve access through RBAC, or role-based access control, which I'm not going to go through today since it differs from one setup to another, and since I assume that you already figured it out. More importantly, some later components might remove the need for anyone or anything to have write access to the cluster. So you might not even need it. We might come to the conclusion that only read access is required. So let's switch to policies. The first thing we need to decide is where to enforce policies. We can have them in a web UI, in a CLI, in a VS Code extension, or in any other place from where users interact with our platform. All those should have some form of a validation, but not as an assurance that only correct definitions are processed by the platform, but for user experience reasons. All those are optional. The mandatory place to implement policies is the platform itself. So that's what we'll focus on today. If that sounds confusing, please watch that video over there if you want to know more about the intersection of policies and user experience. Since our platform is built on top of Kubernetes, we should leverage admission controllers, which in a nutshell are webhooks fired every time we submit a request to the Kube API. And there is a video for that one as well. So we can implement admission controllers with quite a few tools. We can use Kyverno, my favorite, or OPA with Gatekeeper, or KubeWarden, or one of quite a few other solutions or tools that provide policies. Moreover, since recently, we have Kubernetes validating admission policy baked into all clusters. It's not as feature-rich as other solutions, but it is a good starting point, especially since it's already inside our clusters. And that's the one we'll use today. Here's an example. That validating admission policy will reject app claims resources unless scaling enabled is set to true and scaling min is greater than 1. Further on, we are binding that policy to the A-team namespace. So let's apply it and try to apply our application again. This time the request was rejected since it failed the first policy that forced us to enable scaling. Let's fix that and try to apply it again. It failed again, but for a different reason. This time it rejected it because the scaling min parameter is not greater than 1. Let's fix that one as well and apply it again. And this time it worked. We have policies that prevent people from applying our services with values that are not allowed. With developer platforms, we are enabling people to get where they need to be. We are not taking them there ourselves. We are making roads that can be used by anything that passes certain standards, like cars, motorcycles, buses. Our services are those roads, and user interfaces are vehicles. We might create a vehicle or two, but that's not our main business. Roads are. We are in the business of making roads. As a matter of fact, we managed to go through the whole platform without using a single custom user interface. We did everything we need to do without a custom web UI, without a custom CLI, without a single VS Code extension or anything else. It all works because there are many tools that can interact with our platform API. That can be something as rudimentary as URL or kube control or anything else. People using our platform already have plenty of choices how they can interact with it through its API. That being said, if you want to go an extra mile, we might create an interface, or maybe two. That can be, for example, a custom CLI. For those who want a platform-specific experience from a terminal, we can create a CLI. We can do that by writing it in Bash, or going down the proper programming route by using Go, or Python, or Node.js, or whatever we're comfortable with. Or we can pick something more obscure, like Nushell, which I'm using today. Here's a list of available commands in platform, which is a custom CLI I made with Nushell. From here on, people can choose any of the available commands and execute it. For example, if they would like to get all the information about the app claim we applied earlier, we can just execute platform describe resource app claim CLI in the namespace ateam. To be clear, I will not go into more details about creating a CLI with Nushell, since I already covered that in that video over there. Now, before we move on to a second user interface option, let's use the same platform CLI to delete the SQL claim and the app claim. Another option for a bonus user interface could be GitOps. It is a user interface that does not even interact with the platform directly, at least not when operations are concerned. It does have a graphical user interface, but only for observing the outcomes. Today we'll use Argo CD, which is probably the most commonly used GitOps tool, but certainly not the only one. We can also use Flux or Rancher Fleet and a few others. So here it goes. First, we'll go back to the IDP full app repo. Since we already made a few changes to the application repo, we can simply add, commit, and push them. Next, we'll need an Argo CD application definition. In a nutshell, that application will ensure that whatever is in the apps directory inside the IDP full app repo will be synchronized into the cluster. That repo contains the desired state, and it's up to Argo CD to convert it into resources running inside our cluster. By the way, those resources inside the cluster, they are the actual state. So let's apply it and open Argo CD Web UI to see what's going on. We can see that Argo CD detected manifests containing app claim and SQL claim manifests and synchronized them into the cluster. From there on, Crossplane composed managed resources that constitute low-level details required to run applications and database servers. With Argo CD, we got two new user interfaces. First, there is Git, where people store the desired state of the services they want to consume. Then there is Web UI, where they can observe the actual state of those resources. However, we might want to have a Web UI from where people can both define and observe services. While CLIs and IDE extensions and other means of interaction with APIs are great, many people prefer Web UIs over any other interface. There's something attractive to having lots of colors and buttons to push, while at the same time we are presented with experience tailor-made to our needs. Fortunately, there are many tools that can help us create a platform portal. If you're looking at portal as a service solutions, there is Port and quite a few others. However, if you look at open source options, there is one above all others. That one is Backstage. It is in the CNCF Foundation, it is extensible to plugins, and it has a massive number of contributions and adopters. That's the one we'll use today. Let's run it using the CLI we explored earlier. We can see right away on the home screen that it ingested the Crossplane claims we applied through kubectl and Argo CD. That's made possible through a few plugins that I explored in that video over there. So we won't go into details here. If, for example, we enter inside CLI claim, we can notice two Crossplane specific tabs. So let's select Crossplane resources. We can see the claim and composite and managed and other type of resources composed by Crossplane. We can see YAML definitions and events for each. Similarly, we can also select the graph view. Over there we can see pretty much the same information, but this time organized in a graph. Finally, and probably most importantly, we can create new resources based on the CRDs in the cluster. Backstage already retrieved the schemas and converted them into its own templates. If you would proceed by filling in all the fields on all the template screens, Backstage will ultimately generate a YAML manifest and push it to Git. Argo CD in turn would detect changes and synchronize them with the cluster. If those resources are managed by Crossplane, it would compose all the low-level resources, no matter whether they should be running in a Kubernetes cluster, a hyperscaler, or anywhere else, or anything else. Finally, Backstage would close the loop by ingesting data from the platform and show it to users. Try it out. You'll see that's what will happen. Or alternatively, as I already mentioned, watch that video. It's awesome. So, what's missing from this setup? I think I covered all the most important pieces of the puzzle, but there's always something missing. I would like to keep it alive, this project, this repo, this video maybe, by adding other components. Alternatively, I could make a similar setup with different tools. Ultimately, this might become a project on its own where people can select types of components they would like to include into the platform and select tools with which to implement each of them. Maybe, who knows? I'd love to hear back from you, so let me know in the comments. Until then, thank you for watching, see you in the next one, cheers.